Okay, I guess we can start. So, I have this Pinterest board. It's called Code in Movies. When I see some code in a movie, I take a screenshot, I post it there, and I try to explain what it does. And usually, it has nothing to do with the movie. It does something completely different. And we know that, right? That programming, engineering in the movies, in reality, they're not the same thing. So in the movies, the superhero can build this thing in a cave using just a bunch of scraps. And in reality, well, in reality, we are actually drowning the planet on electronics waste. And on the other side, when we need to do something simple like turning on and off a light, opening a door, we do not reach for the scraps. We buy new stuff. We buy a microcontroller, an Arduino, a Raspberry Pi, we write some firmware. And then, well, then it gets worse because once you have it working, don't you want to control it over Wi-Fi? Sure, you buy more new stuff. Or maybe you want to control it with an SMS. Well, you buy more new stuff. And don't you want a display on that thing? You buy more new stuff. And at the same time, as an Android developer, you probably have a growing stack of old phones and tablets. And they already have all that and more. They have Bluetooth, they have a real touch screen. It's just that they cannot easily interface with the physical world. So, well, they sit there, they collect dust. They wait to become electronics waste. So my goal today is to bring fiction and reality closer together and turn you into superheroes, or at least action heroes. So your mission, should you choose to accept it, as they say, will be to control this small electric motor that I got from scraps, of course. And it's powered at 12 volts, and you can only use your phone or a tablet, but nothing fancy, just a regular phone, no routing, no custom ROM, nothing, just your phone. And a bunch of scraps, things that you can find in any dumpster. And you cannot write any firmware, you can only write some regular Java code. So before we start, just a word of caution. Being smart is better than being a superhero, so don't do industrial controls using scraps, okay? It's okay at home if you want to play around with things, and it's also a great learning opportunity. We always learn a lot by hacking into things, in the original sense of the term, which was to overcome the limitation of things, to combine them in unexpected ways. And sometimes what we learn by doing that can also be useful in our day-to-day job. Sometimes it cannot, but anyway, it's fun, so yeah, let's just do it. Just be a little careful, okay? Now, there is no chance that whatever we're going to build will explode in your face or anything like that. That's a level of user experience nobody ever talks about. But yeah, whenever electricity is involved, just pay some attention, okay? So, well, the first step before we can control the electric motor is that we learn to control an LED using just our phone. And well, that's pretty much what people do with an Arduino anyway. They learn to blink an LED, then they lose interest. But yeah, for us, it's just the first step, and we need to do that using just scraps, just our phone and some scraps. So how do we even approach that? Well, the most straightforward idea will be to use just one of the built-in LEDs. Yeah, that works, it's simple, it's effective. And I will suggest that if you plan to reuse a very old phone, because at some point we need to attach wires to that LED, so it will require you to solder on your phone. So yeah, it's an option, it's a valuable option, I just didn't go that way. So another option is to connect something to the audio jack. That's very flexible. It has been used in a number of hacks to do, for instance, universal remote controls. But to be honest, I wasn't overly fond of the idea of using something that is analog in nature, like audio, to control something that in the end will be digital in nature, an on-off switch for an electric motor. So again, it is a valuable option. I just didn't go that way either. So we are left with a USB. Now, most phones and tablets have a working USB. By that I mean it can be used for more than charging, it can be used to transfer data. We also throw away a lot of USB stuff, so that looked like an interesting combination if we want to reuse scraps. So where do we find LEDs in common USB scraps, things that we throw away easily? Well, many flash drives have an LED. A lot of printers have an LED, and it's easy to find
an inkjet printer in scraps, because at some point people realize that ink is being sold for more than the printer, and they throw away the printer. And also, any optical mouse will have an LED, and most keyboards have LEDs for caps lock, scroll lock, and stuff. Now, the problem with most of those devices is that there is no standard way to control the state of the LED, assuming it's even possible. So even if you get it to work with one specific device, there is some chance that it's going to work only with that specific device, that like specific printer. That's not so good. Except the keyboard. The keyboard is the real winner here, because LEDs in a keyboard are host controlled. It means that when you click on caps lock, it's not the keyboard turning on the LED by itself, it's the computer telling the keyboard to turn on the LED. And it does that using a standard protocol. So what we do is going to work on any USB keyboard. Also, the LEDs in a keyboard, well, they tend to last longer than the rest of the keyboard, and exactly because keys tend to wear out, it's very easy to find a USB keyboard in the scraps, maybe half working. This one that I used, I had accidentally poured water on it, so it wasn't working too well, but the electronics was fine enough for this application. And by the way, this is the size of the board inside the keyboard. Once you remove all the connectors except the USB cord, everything else, the size is very small, so we end up with something small, lightweight, which is also good. So now the first step is to connect the keyboard to the phone, and you probably know this already, but your phone is normally a USB gadget or device, so you connect the phone to a computer, the computer is the host, the phone is the gadget, and you see that as a mass storage of some kind. But a keyboard is a USB gadget as well, and you cannot connect two gadgets together. So we need to turn your phone into a host, a USB host. And to do that, you need an OTG adapter. OTG stands for on the go, and it looks like that. You probably have one already. If you don't, this is probably the only thing that I will suggest you buy instead of making it, because it's very cheap, it's generally useful. But if you want to make one from scratch, it's very easy. You take a female from one of those useless USB extension cords. They used to be sold with flash drives and something like that. Nobody ever used them. And then you take the male from a data cable, and then you need to add a pin between a wire between pin 4 and 5. In fact, the female, the type A, has only 4 wires, but the micro USB has 5, exactly to support this on-the-go switch between device mode and host mode. So that extra wire between pin 4 and 5 is telling your phone to switch into host mode from the usual device mode. In what follows, I will be using a commercial OTG adapter, so if you see pictures, I didn't make one. By the way, you don't really need the female. If you're willing to remove the USB cord from the keyboard, or what is left of it, you can just solder the micro USB male there and add the wire between pin 4 and 5, and you will have a board that automatically switches your phone into host mode. Okay, we are going to get back to hardware because we need to control the motor in the end, but before we do that, we also need to write some software to control the state of those LEDs. And before we can do that, it's useful to know a bit about USB, about the way a USB device presents itself to the host. Now, a USB device can describe itself in a sense. So it all starts with a device descriptor. That's also a class in the Android APIs. And a USB device can also be composite. So you may have a keyboard which also have an integrated trackable. So I'll use that as a running example. The next layer will be that of configuration. We cannot see that in Android, but a USB device may support multiple configurations. Suppose that our keyboard plus trackable can be USB powered or can be solar powered. And when it's solar powered, it will disable the trackable just to save energy. So those will be 2 alternative configurations, but we do not get to see that. We go straight from device descriptor to interface descriptor. So we only get to see the active configuration, the configuration that is active at that moment. What is an interface? An interface is a logical interface, because the physical interface is just one, of course, is the USB. And in our case, we probably have one interface for the keyboard, one interface for the trackball. And finally, inside an interface, we have endpoints. Endpoints are the actual channels that we can use to send and receive data from and to the device. Endpoints have a direction, And the direction is from the perspective of the host. So when we see an input, it means the phone, the host, can read from that, okay? Now, all the stuff in green, if you're not colorblind, everything except configuration, is accessible from the Android APIs. So before you write any code, when you want to play with a new USB device on Android, I always suggest that you download one of the many free applications from Google Play that can simply dump all the information from those classes. It's very easy to make one. You go through all the device descriptors, then all the interface descriptors, then all the endpoint descriptors, and you dump whatever information Android knows about those. But yeah, you can also get a free tool. And now, if you connect your keyboard to your phone and use one of those apps, you're going to get something like this. Maybe not identical, but some point will be the same. Now, my keyboard had two interfaces. Your keyboard may have only one. What is important here is the part in red. You see that we get to see endpoint 1 and 2. This is the actual number inside the endpoint descriptor, okay? You also see a number 0, but that is just the index in the array of endpoint descriptors. It's not really useful. So this application is dumping that also, but what is important is that 1 and 2. We'll see why it's important in a moment. The problem is they are both inbound. That means we can read from those endpoints, which makes sense because you type on a keyboard, you want to read the keys. But to set the state of an LED, you want to write to the keyboard, you want to send data to the keyboard, and you cannot do that through an inbound endpoint. That's a bit of a problem, and that's usually where people tend to stop. When I had this idea of using the keyboard to control the LED and then the motor, I Googled for it, because it doesn't make much sense to redo something other people have already done. And I saw a few guys had this idea, we can control the state of the LED, and they gave up at this moment. And they also made up explanations. Sometimes we do that. They say, oh, Android must be hiding the endpoint, stuff like that. And so this is the moment where you need to know what the specification says, and you need to know the APIs a bit, and then you can move past this problem. So if you, yeah, it's a mouthful, but if you read the USB device class definition for human interface device firmware specification, is a long title, and section 4.4, it says that if there is no interrupt out endpoint, this is our case. We only add interrupt in endpoint. We add no output endpoint. Then output reports, that's standard language for stuff you want to send to the keyboard, are transmitted to the control endpoint. So good, we need the control endpoint. What's the control endpoint? You keep reading and you discover that endpoint 0 is the control endpoint, except that we only had endpoint 1 and 2. Why is that? Because endpoint 0 is assumed to be there, is always there, so it's not enumerated in the descriptor. But Android is giving access only to what is present in the descriptor. So that's the mystery. It's not that it's hiding something, it's that the device is not enumerating it because it's assumed to be there, and Android is not enumerating it to you. So we still have a problem because there is no API to go to Android and say, well, I know you have endpoint 0 somewhere, just give it to me. So that seems again like a showstopper. But there is this nice API. The class is USB device connection and the method is control transfer. And if you read the documentation for that, it says performs a control transaction on endpoint 0. So that's it. That's the way we write to the keyboard. We do not get endpoint 0. We get a connection to the device and then we use control transfer to send data to the keyboard. But send what exactly? Now, many times we tend to think in terms of a binary payload that we send to the keyboard, a buffer of data that we send. But for reasons that will be clear in a moment, it's better to stay with the documentation, with the standard documentation a little longer. And as usual, the standard is not easy to read. You have to jump around a lot between the paragraphs. And in section 722, it described this idea of a set report. Now, in this standard for all the human interface devices, so keyboards, mouse, whatever, they call report whatever you exchange with the device. And when you want to set something, you send a set report message. This is a set report message. It is made of parts. Each one must have a value. So BN request type, you look around, is 21 hexadecimal. Set report is a constant. You look around. You look back actually in section 7.2 is just 9. And then we need to figure out the value of this for a keyboard and LEDs, because this is a universal message. If you want to send something to any human interface device, use this message. So we need to understand the value of those for a keyboard. And you actually have to go down to appendix B.1 to find it. But in the end, data is just 1 byte. And in that byte is a bit mask. So bit 0 is the state of numlock, bit 1 is the state of caps lock, and so on. So you cannot set the state of a single LED at once. You always set them all at the same time. And well, the other stuff is just a matter of reading the documentation very carefully until you find all the right values. Now, an alternative to all this reading, which is also more in line with hacking, is just to capture the USB traffic. You attach a keyboard to your computer, you sniff the USB traffic, you click on caps lock, and you look at whatever is being sent on the USB. That's the magic set of values that you need. But as I have anticipated, well, it's useful to know all the parts, because when you look at the actual signature for control transfer, it mimics set report very closely. So request type is BN request type is 21. The request is B request is 9, and so on and so forth. Data is a buffer with 1 byte inside, is the bit mask. Length is the length of the data, is 1 byte. And well, timeout, I use 1 second, because if it cannot set the state of an LED in 1 second, yeah, we do have a problem. So I set 1 second. And so we're going to see more code, but in essence, what you need to do to set the state of the LEDs, if you have a bit mask, is something like this. You start with a bit mask, you create an array with just a bit mask inside, and then you use control transfer with all the right values, and it will work. So, well, let's see some more code. I'm not going to give you a full tutorial on how to open a USB connection and stuff. There is a lot of material on the internet on that, including tutorials from Google. But in essence, again, you grab the USB manager, you find the right device. I'm being lazy here, so I just get the first device. Okay, if you can connect more than 1 USB device, which you can, you should look for the right one, like using the manufacturer or the device class or something like that. I just get in the first one, and I ask for permission to use it. Now, Android will ask the user if my app can use the USB device. On confirmation, I get an intent. I extract the device from the intent. I now have permission to use it. And sorry guys, I still like object-oriented programming, so I build a keyboard object of a USB keyboard class that I have created. And my USB keyboard has its own thread because it's doing I/O on the USB, so it's doing that in its own thread. And when some other thread, like the user interface thread, wants to set the state of the LEDs, it will just put a bit mask in a queue. So my thread will dequeue that and write on the USB. So this is the linked blocking queue where requests are sent. And this is the connection. This is how you get the connection to do control transfer. You just open the device. And this is weird in a sense. Now my code, my application works without those 2 lines. So they are not required because I'm not using an interface, I'm not using an endpoint, I'm just using endpoint 0 from the connection. And still I'm using those. Anybody can guess why? It's not a easy question, I think.
Create a lock on interface.
Yeah, but why?
Because anyone else
Okay, it's almost like that. It's not really that I want to prevent other applications from using it, which will make sense anyway. I want to prevent Android from using it because Android knows how to use a physical keyboard. So the moment you plug in a physical keyboard, it will display a small icon on top, like a keyboard, and will stop showing the soft keyboard. But our keyboard is no longer a keyboard. We have removed all the stuff. It's pretty much a bunch of I/Os. So I don't want Android to think it has access to a physical keyboard. So by grabbing the interface, Android will say, okay, hands off, I no longer have the keyboard. It will hide the icon, will keep using the soft keyboard again. Okay, so that's the purpose of that. But also preventing other applications from using it will be a reasonable answer. But my biggest concern was with Android itself. Okay, I also start my own thread, which, well, it's quite simple. It's waiting on the queue. taking a bit mask from there, and apart from termination, it's just using the control transfer to just set the state of the LEDs. And a simple user interface with 3 checkboxes can do something like this. When the state of a checkbox is changed, you need to recalculate the entire bit mask because you need to send the entire bit mask. And well, then I want to put that into the queue, but I don't want the UI to know that there is a queue in between. So I just call a method in the keyboard. The keyboard has this power LEDs from mask method. It will just put the bit mask in the queue. Then the thread will dequeue it and apply it. And it works. So you see it's quite small once you have removed all the stuff, and the state of the LEDs will reflect the state of the checkboxes. So it's one step. We can control the state of an LED using just a half-broken keyboard and the phone. Now, before we move further, because we want to control the motor, right? It will be useful to know how fast can we turn those LEDs on and off. When you hack something, it's always useful to know the limits of what you are doing. So, well, from a software perspective, it's quite simple. I just need to change my I/O thread, the one that was waiting on the queue, with an infinite loop like this. I use 2 bit masks. One is all off, one is a single LED on. And then I set those bit masks continuously. No waiting, no sleeping, no nothing. The system is still responsive because we're mostly doing I/O. So this is as fast as possible. And how fast can we go? Well, normally to check the speed of that code, you might be using a profiler or a timer. But we are hacking with electronics anyway, so I used an oscilloscope. And well, according to Hollywood, if you are a superhero, you need to use a vintage oscilloscope. You can see it well, but that's a fantastic for the Iron Man, even Star Trek Enterprise, or just the Big Bang Theory. They all have a CRT. They never use an LCD modern kind of thing. So me too, I want to be a superhero. I use this. And the only downside was that I had to take pictures with a camera because I couldn't save a screen dump with a click, but okay. So if you connect the oscilloscope to the LED, what do we expect? Well, we expect the signal to be on for a while, then off for a while, then on for a while, off for a while, and that while is pretty much the duration of the API call. So ideally, it will always be the same duration. It's always the same API call over and over. Well, now we know that won't be true, right? Because Android is not a real-time operating system, so if the wrong process or thread is scheduled at the wrong time, it will change the timing. So we have to expect some jitter, okay? But pretty much we should expect something like that. But Broken Dreams, this is what I got instead. And yeah, it looks a bit like Arnim Zola from Captain America, but yeah, it's not what I expected, really. So I moved back to the original code, the one where I could see the state of the LED in a stable on state, stable off state, and check the signal. And this may not apply to your keyboard, but in my keyboard, the signal in the on state was indeed stable, a flat line, but in the off state, I had that kind of high frequency noise. So, well, it was just noise, so I suppressed the noise using a resistor applying a load. I'll show you how and where I got the resistor from in a few slides. So, well, anyway, after that, the signal was clean. It was not square. You can see major differences in durations, but it was clean. So, guess the frequency. Before you guess, the actual time it takes between an on and off is the time it takes from the moment you call the API. You need to go down to Android, down to Linux, on the wire, up in whatever USB stack they have on the keyboard until the LED is toggled, okay? So guess how many times per second we can do that, like 100,000, 10,000, 100,000? Wild guess, just like 2,000 or like 2 per second? 2 per second, okay. This is very pessimistic. Okay, now this is another vintage tool that goes well with the oscilloscope. And it shows that on my device I could do that at 1,000, well, the frequency was 1 kilohertz. That means 2,000 API calls per second, because one period is 2 calls, is on and off. So 2,000 API calls per second. You were almost right, just a matter of zeros. And the problem is it's really unstable. The next moment it was more like 700 hertz. So, conclusion from this little detour, what we have learned. Well, something very useful. We discovered we had noise and we removed it, we killed it. We know that there are things we cannot do with this technology, like anything that requires high frequency and low jitter. Like if you want to do a universal infrared remote control, you cannot do that with a keyboard. Also PWM. It's not that you cannot do that with scraps. You cannot do that with a keyboard. Maybe other kind of scraps will do. Things that you can do, turn on and off stuff at low frequency like we wanted from the very beginning. We want to turn on and off the electric motor. So let's get back on track. Now, we cannot just remove the LED and put the motor in its place because, well, we have a problem with voltage. The motor was powered at 12 volts and the keyboard is currently powered through your phone, through the USB, and it's not 12 volts. Also, the keyboard is not willing to provide enough power or enough current to power the electric motor. So we have a problem there. And also, we have a problem with isolation. Right now, the LED is electrically connected to your phone. So whatever happens there happens to your phone. You have a short circuit there, you short your phone. That's probably not what you want. So the next step is to add galvanic isolation. And we have a few ways to do that. The simplest one is to use a photocoupler or optoisolator. It's the simplest one because it's a very common component in stuff that you can find in scraps. In every power supply, in every charger, you will find one. So this is a power supply for a fax. You may remember that thing from the past century. And the white component covered in alien slime is the photocoupler. And this is more recent, is the charger for notebook. And well, right there, you cannot see it well, but we can zoom in. You know what they say in movies at this point? They say enhance, and the image gets better. I tried some image processing, but doesn't work too well. Anyway, that's the component we need to use. And I'm going to be using this because the board has less components, so it's a bit more challenging because at this moment, you also need to recover a few resistors. So the value is not really mandatory. I used a 12 kilo ohm resistor to suppress the noise and two 1 kilo ohm resistor to limit current in the photocoupler. I'm going to show you the circuit in just a few slides. So, well, when you are here, just recover a few resistors. We're going to use them. Okay, so if you're more of a software guy and not familiar with a photocoupler, this is how photocoupler works. It's like having an LED and a phototransistor in the same chip. So we are going to connect the LED, the internal LED, in parallel to an existing LED on the keyboard so they will turn on at the same time, okay? Now, when the LED inside the photocoupler turns on, of course it emits lights, except that you can't see it because it's inside the plastic, and will make the phototransistor conductive. So pretty much current here, current here. Except that two sides are electrically isolated because, well, in a sense, we are using light to transfer information between the two sides, okay? Now, I actually found a data sheet for this component I reused because I wanted to show you that the maximum current we can draw from the phototransistor is too small. It's just 50 milliampere. So that's not enough for our motor. So it's one step. We have galvanic isolation, but no joy yet. We cannot just plug in the motor. And actually, we have two problems. This is pretty much like when you have a level indirection in software. You know, when you have two concrete classes and you put an interface in between, and now you have a different problem. Who is going to create an instance of the concrete class? And then you need a factory and all that stuff. And this is not so different. We have a component in between. We have a level of indirection between the phone and the motor, providing galvanic isolation, but now we have two problems. One is, who is going to provide voltage and current on the other side? Because one side is powered by your phone, just like the LED. We connect that in parallel to the LED. The other side is decoupled. So who is going to provide power on the other side? And two, we have just seen that that phototransistor cannot power the motor anyway. So yeah, we need to solve both using scraps. And we are lucky though, because there is just one thing that will solve both at once. And that's an ATX power supply. You may have kept one just in case, so this will be the case. And if you haven't, this is where you find it. It's the ATX power supply for any desktop computer or even a server. Now, some of those ATX power supply, they have a physical switch on them, but even if you physically turn them on, when you look at the connector, you don't get any voltage. You don't get any voltage because they always start in standby. To get some voltage, you actually have to connect together the PS on and COM pin. Now, that's what the button on your computer does, by the way. Okay, it moves from standby to power on. The good thing is that very little current has to go through that connector. So that's the perfect job for the photocoupler. And okay, believe it or not, we have all the ingredients. We just need to plug everything together. So let's see how we do that. It's quite simple. Do one step at a time. This is the keyboard. You can leave the LED on. You don't have to remove it. Okay. This is the resistor that I used to suppress the noise. I use 12 kilo ohm, other values will do as well. This is a 1 kilo ohm resistor that I use to limit current in the photocoupler. And this is the photocoupler. So all this stuff is coming from the charger for the notebook, so it's all stuff that we can reuse. We connect the phototransistor to the ATX power supply, COM and PS on. Now polarity matters, so make sure you connect the emitter to the COM because otherwise it's not going to work. And we need to limit current there as well, so this is 1 kilo ohm resistor as well. We connect the motor to the 12 volts, we provide line power, and magically it works. I'm going to show you. This is how I put it together. I use a piece of scrap strip board. Looks a bit crappy. Yeah, I can do better than that, but you're supposed to do that in a cave, so it's okay. And it's just a few wires, so you can just solder things together in a dead box style if you prefer. And what is important is that it works. This is, okay, all the stuff, the phone, the keyboard, the motor with something that will show you that is moving, hopefully. Okay. So, yeah. It works. We can control the motor using just our phone. So, in a sense, the mission is complete. But you know the movies, when you complete the mission, it's never completed. You have something else to do. So, we still have the time for a little more. And what about inputs? If you buy a microcontroller, you also have, among other things, you have digital inputs. What about us? Well, it's a keyboard, right? So, we should get inputs for free, in a sense. So this is how a keyboard works. It's just a matrix. It's wires in rows and columns. When you click on a key, you make a row and a column touch, and that will generate a specific scan code. Okay? Now, rows and columns are somewhere there. It's just not clear which is which, so we need to find out. And that's pretty simple. We need some software. And this time, I'm going to use the endpoint. I'm going to use the endpoint because I want to read from the keyboard, and the endpoint was the input endpoint to read from the keyboard. So I get the endpoint, and then for simplicity, I changed my I/O thread again to read from the keyboard. Now, I'm not going through all the standard specification this time, but whenever you click on a key, you always get 8 bytes. They waste a lot of stuff. So the first byte is a modifier, is a bit mask again. Is the state of Control, Alt, Shift, all those things that can modify the other keys. Then 1 byte is reserved, and then you have up to 6 simultaneous keys if your keyboard can support that. Okay? So in this code, I'm just dumping on the logcat the first non-modifier key that you press if you have a keyboard, or that you find when you find the right row and column combination just by trying out. And this is how you can try that. You can barely see the phone, but it's there, and it's connected to the computer using Wi-Fi because the USB is busy, is powering the keyboard. And then I just put a clip on a random pin, and I move the other side on other pins, trying to find a row and column combination. When I find a row and column combination, I get something on the logcat. I hope you can see that, maybe not the exact scan code, But as you move it, you get scan codes. That means one is the row, one is the column, or vice versa. You don't know which is which. But anyway, you know that if you make these two wires touch, it will generate a scan code. So you can use that as a digital input. And so maybe you didn't see it, but I had a resistor at the end of the wire. Because the first time I did that game, I didn't put one there, and I shorted my phone. So yeah, you need something there. You need galvanic isolation on the input. We had galvanic isolation on the output with the photocoupler, but we do not have one on the inputs. So, well, you know how to do that, right? So it's left as an exercise. No, I'm just kidding. This is how you do it. You get a photocoupler, and you put a resistor, let's say 1 kilo ohm, that will limit current in the LED inside. That will be your digital input. And the other side, remember, when there is 1 at that pin, the phototransistor will be conductive, so it will put together a row and a column if you find the right connector. So you get the scan code. So you find 2 pins, you know that for these 2 pins you get that scan code, you connect this, and when you have 1, you get that scan code. So it means you can have a lot of scan codes because every key has a different scan code, so you can have a lot of digital inputs from your keyboard. And okay, we still have the time for something that is not going to be easy, and is charging while in host mode. Normally your phone is charging from the USB, but right now the phone is powering the keyboard, or the X keyboard, now a bunch of IOs from the USB. So it's discharging, and that's not good if you want to leave that on like forever. And so we need to provide power when we are in host mode. And theoretically, you can use this. It's called a Y OTG cable. Y because of the shape like a Y. And so you put, well, the female will be for the keyboard. The micro USB male is for your phone. And the male type A is for the charger. And that's part of the OTG specification. They have this idea that if instead of a wire between pin 4 and 5, you put a resistor with a specific value, 36.5 kilo ohm, your device can turn into host mode, and we need that, and still charge from the USB instead of powering the gadget from the USB. Now, some of those cables, they're very cheap, but they're fake. That means they do not have the resistor inside. They just have a wire, so they don't really work. You have to fix them. You have to cut them open and add the resistor. So this may or may not work on your phone. If it works, you may even want to reconsider the ATX power supply. Because when I said that you don't get any voltage when it's in standby mode, I lied. You actually get 5 volts on that 5 volt standby pin. Not much current though. So you may come up with something that will power your phone in standby from 5 volts standby, or when it's on from the regular 5 volts, and also power the motor with the same power supply. Just be careful if you do, because then you have common grounds between the 2 sides of the opto-isolator, so do that if you know what you're doing. Otherwise, use a charger connected to your phone. Now, if the Y cable doesn't work for you, the first step is that you try different resistor values with a trimmer or something. A lot of tablets that are sold with custom docking stations, they don't use the standard value because that will force you to buy the docking station. So if you try different resistor value, you might find one that will switch into host mode but still charge from the USB. And some phones and some tablets are more picky than that. They want a square wave on the power line before they turn into host mode while powering from the USB, again because they want you to buy some hardware from the manufacturer. So in that case, it's more complicated. You may want to remove the battery and power your phone from there, okay? That can be very easy or very complicated depending on your battery, because some have an intermediate pin to give the power, the charging level of different cells. Others have a temperature sensor, so yeah, it can be complicated. So we do not have time for that. Maybe another time for more surgery on your phone. So, well, I guess that's it. This is my email, my Twitter handle, one of my websites. I do a lot of stuff on Android. I don't work just with Android, but I do a lot of stuff on Android, mostly custom devices, interfacing with custom devices, or porting Android to custom devices for vertical applications. Massive changes into the Android core. So yeah, if you have some impossible project, you may want to get in touch. And I think I still have a little time for questions. So if you